then what's left is rho k to the minus 2. Okay, and well, this is just from here, and then differentiate f with respect to rho for this highest term. Well, that'll just give you k rho to k minus 1. Well, that's the same. And f, well, you just that highest power. Now have a look at this. Now you've got a what's the highest power of rho in this line? Well, here you've got k to the minus 2. From here, the 1 here, that gives you a k to the minus 1. Well, that's a higher power than this one. And then the rho underneath, that would take this to k minus 2, so that's not. And here you've got k to the minus 1 from here. Right? Now, if you go to the next smaller one, so rho to the k minus 1, and you, it'd be like your polynomial will be of the form rho to power little k plus a, constant, rho to power k minus 1 and so forth. Well, the term in your f, rho to k minus 1, it will not affect its biggest term would be k minus 2. So that's not going to have any effect on these terms, rho to k minus 1. Now, since this whole thing has to be 0, the coefficient of the term rho to k minus 1, that coefficient has to be 0, right? I mean, if you knew what the polynomial was, all, for this equation, all the coefficients of the powers of rho in this left-hand side, they all have to be 0, including the coefficient of rho to the k minus 1. Okay. Okay. So which term? So that coefficient has to be 0. So what is that coefficient? So the coefficient of rho to k minus 1. What is that coefficient? Well, you've got a minus 1 here, k, so minus k, and you've got another one here, because that's, these two, that gives you k minus 1. You've got another one, lambda minus 1. So, in other words, minus k plus lambda minus 1, minus k plus lambda minus 1, that's the total coefficient. All the terms, all the coefficients of rho to k minus 1 added together, and that sum has to equal 0. So you just get this, right? And therefore lambda equals k plus 1. Take the k and the 1 over the other side. So lambda equals k plus 1. For what values of k? Well, k is your highest power of the highest term in your polynomial f. So I mean, you could start at 0, right? You could have just a constant. Now that's a polynomial. This is the 0th order, but it's a polynomial. So your k can start at 0. Okay, so k goes 0, 1, 2. That's a bit inconvenient. So let's just let's rewrite this. K is just integer. So let's just rewrite this as lambda equals n, but n starts at 1, not 0. Okay, so n is 1 larger than k. Right. So lambda now, we've deduced that lambda is equal to an integer, a non-zero integer, starting a positive integer, starting at 1, 2, 3, the natural numbers. Okay. Now, what is lambda? Well, here's lambda. We defined it to be this. Oh, so now this lambda here has an alpha in it. Okay? And what's alpha? Well, alpha squared is a function of the energy. Aha! So, you can see the logic. The lambda has to take on positive integer values. Right? Lambda has to be an integer. So that's an integer. So we can solve for alpha. And if we know what alpha is, we know what the energy is. Ah, Okay, so we have found a way to find the allowed energy for the hydrogen atom. Ta-da! You know, that is a big deal, right? And here it is. Again, homework. I'm asking you to do the details. Right? So, you know, put an n here. So that gives you you can solve for alpha, and from alpha, knowing alpha, you know what the energy is. So using this relation, and this relation, put those three together, and I'm asking you to calculate the value of the hydrogen atom energy, right? E to the n, depending on your n. Now, why is it minus? Well, it's a convention. The e to the n is negative because the convention is, in terms of the potential. How do you define that? Well, the convention, a custom, because that's all it is let the potential be zero at infinite distance. Right? As you bring the particle in, the potential does it increase or decrease? Depends on your sign. But we just take the convention. The potential is zero at infinity, right? And as you get closer and closer to the nucleus of your atom, the potential will change, of course. Okay, so calculate those energy levels for homework. Now, you've now got all the because of the radial symmetry of your potential, your V is only a function of R, and it's not a function of your angles, and that makes sense because what is generating this potential? Well, it's the nucleus of the hydrogen atom, right? And that's effectively a point, and it's the charge on the nucleus that's creating this potential that the electrons feel as they whiz around. So these energies, they will be independent. Is that true? Be careful what I say. Of the angles, theta and phi. They depend on the radius only. Right. Now, you got all the range here, all possible ends. Now, can you see? Now we can bring in the correspondence principle again. Think about it. As n gets large, the difference between En and En plus 1 will be very, very small. Because n goes large, this energy here becomes very small. And so the difference between them becomes very, very small. Okay, so effectively your energy differences, the size of the quantum jumps, the quantum values between two energy levels goes to zero as n goes very large, and hence you get like continuous energy levels, allowed energy levels. They become effectively they can change in lumps as small as you like, so effectively continuous. So this formula here, using the correspondence principle, the energies become continuous. But for n small, then you have very discrete energies, right? And the energy value is proportional, because all these constants, is proportional to 1 over n squared. Ding! Ring a bell? That's Bohr, Niels Bohr's prediction, right? In 1913, I think, that got him the Nobel Prize, right? So here now, using Schrodinger's equation, we arrive at a similar prediction that the energy of the electrons in the hydrogen atom, moving around the nucleus, have this quantized energy, and that fits perfectly with Bohr's model, or turning it the other way around. Bohr's tentative suggestion is now confirmed by a much more rigorous and more powerful mathematical technique, which is Schrodinger's equation. So in a sense, the Bohr atom of the model is a consequence, it's a logical consequence of the mathematics coming out of Schrödinger's equation, which is pretty amazing. Right? You know, quantum mechanics is amazing stuff. Right, well, I've run out of board. Now tomorrow I may very probably have my new big board, which whose total area, I haven't calculated it, but it must be somewhere between 1.5 to 2 times larger than this board. So I will be, I'll probably have to develop some new techniques, new style of presentation in these lectures. For example, I'm anticipating dividing this bigger board into sections. So instead of wiggling now, I just put straight lines. Maybe it also looks a bit nicer. Like I say, this whole lecture series is just one continuous experiment. Right? I keep trying things, and like yesterday, for the first time, I started using a black pen. I think the contrast, the readability is improved by that. So you know,
Iris database has been updated.
It never stops. All right. So until next session, where we will continue on with talking about the hydrogen atom, a real physical system, as discussed by quantum mechanics.